In the earlier lecture, we have studied Fraunhofer diffraction at single slit. In a Fraunhofer diffraction at single slit, on the screen, we get principal maxima, minimas, and secondary maximas on either side of principal maxima, as shown in this diagram. In this lecture, we have to find the position of the minima and secondary maxima from center of principal maxima. What you see in this diagram is this is the wavefront and this AB is the slit. There is a lens and on the screen you see the diffraction pattern due to diffraction at single slit. And in this case we have to find the position of the first, let us find the position of the first minima and position of first secondary maxima from center of the principal maxima. As you see here in this diagram, at this point you get the first minima. This one is principal maxima. At this point you get the first minima and this one is the first secondary maxima. You get this on either side of this principal maxima. First, let us find the position of the minima from the center of principal maxima. At point P not over here, we get the center of principal maxima. And at the point P1 here, let's say we get the first minima. Now this first minima is obtained at point P1, which is at a distance x. This is the distance x from the center of central maxima, or we can call it principal maxima. And we have to find this x. So the first, let us say that the first minima is obtained at point P1 when the theta is equals to theta 1 and which is at a distance x from the center of central maxima. We already derived the equation for minima, which is a sine theta is equals to plus minus m lambda. Then for the first minima, we are considering the first minima only in one direction, which is at point P1. Then this equation would be a sine theta 1 because we get the first minima at an angle theta 1. So a sine theta 1 is equals to lambda, or sine theta 1 is equals to lambda by a. Let us say that this is equation 1. Then let's assume that the lens is very close. This lens is very close to the slit. That is, this lens is very close to slit. Or the screen is at a far distance from the slit. Okay. If lens is very close to the slit, then what will happen? How much would be this distance? How much would be this distance? If lens is very close to slit. Lens is very close to slit means this lens we are using to focus the light. So when this lens is very close to slit and we have focused the light at point P1 and at P1 we are getting minima. Then how much would be this length? This length would be equals to the focal length of the lens. Okay, when this lens is very close to the slit, then this length is equals to focal length of the lens. Then we can write sin theta 1. Sin theta 1 then is equals to the distance x upon f. F is the focal length of the lens. So f is focal length of lens. And let us say that this is our equation 2. Then from equation 1 and 2, from equation 1 and 2, we can write x is by f is equals to lambda upon a, or this x is equals to f lambda upon a. So using this equation, we can find the position of the first minima from the center of the principal maxima. X is the distance. This x is the distance between the center of the principal maxima and the minima. So for first minima, x equals to f lambda upon a. Then for second minima, it would be x equals to 2f lambda upon a. Similarly, for the third minima, x equals to f 3f lambda upon a, and so on. So this equation is useful to finding the position of the minima. Then in this case now, we will find the position of the first secondary maxima. The first secondary maxima in this case, let's say this is the position. Let's say this is the point P2. So at P2, we get the first secondary maxima, which is of course the center of the secondary maxima. Then the distance, let's say that the distance between the center of the secondary maxima to the center of first principal maxima is equals to x1. And this x1 we have to find. So in this case, the first secondary maxima, which is obtained at point P2, when, let us say that, when theta is equals to theta 2. Now this angle is equals to theta 2. And this point P2, which is the center of secondary maxima, is at a distance, let's say x1, from center of central maxima. Then the equation for secondary maxima, which we have studied in the earlier lecture, which is a sine theta is equals to 2n plus 1 lambda upon 2. Of course, this is a plus and minus, because you get this secondary maximas or principal or minimas on either side of the principal maxima. So this is the equation for the secondary maxima. Then for first secondary maxima, the equation would be a sine theta 2, because the angle in this case now is theta 2. And that is equals to, now there n is the 1, so that would be equals to 3 lambda upon 2. Or we can write sine theta 2 is equals to 3 lambda upon 2a, and let's say this is equation 3. Now again we are going to assume that if the lens is very close to slit, again if this lens is very close to slit, or the screen is at far away from the slit. If this lens is very close to slit, then this distance, let's say this point is O, then distance OP2 would be equals to the focal length of the lens. If that is the case, then we can write sin theta 2 would be equals to x1 upon f. x1 upon f, which is equation 4. F is nothing but focal length of lens. Then by comparing equation 3 and 4, from equation 3 and 4, we get x1 upon f is equals to 3 lambda upon 2a, or x1 equals to 3f lambda upon 2a. So the position of the first secondary maxima is equals to 3f lambda upon 2a. Similarly, the position of the second secondary maxima would be x1 equals to 5f lambda upon a 2a. Third secondary maxima position would be 7f lambda upon 2a, and so on. So by this equation, you can find the position of secondary maxima from the center of principal maxima, and by this equation you can find the position of the minima from the center of central maxima.